So we spent most of the class so far thinking about the question, if we have a function, what is its derivative? Now, in this last chapter, we're going to try to go the other way. If we have a function, what function has that function as its derivative? Okay, that was a little strange, right? Because we're going backwards. But look, this kind of sums it up, all right? The technical term for what we're looking for here is the antiderivative, right? Which we're going to represent with this capital letter F. So cap F of x is an antiderivative of lowercase f of x if f prime of x, the derivative of capital F, is equal to f of x. All right, so what I want you to kind of have in your head here is what we're trying to do is go backwards. I'm going to give you a function, and I want you to think, okay, what function do I have to differentiate to get that one? All right, so let's take an example. All right, I've got f of x equals x squared, and I want to find a function that when I differentiate it, that is what I get. All right, it's a polynomial, right? So I mean, we're gonna just we're gonna do this by experimenting. I'm gonna play around a little bit, see if we can't come up with the answer. So I know that when I differentiate a function, when I differentiate a polynomial, the degree goes down by 1. So if I want to go backwards, I'm thinking the degree is going to have to go up by 1. So let's start with this. I don't know if this is going to work or not, right? We'll test it here. I'm going to say cap f of x is x to the third. Does that work? Is that an antiderivative of f of x equals x squared? Well, I don't know. Let's check. Let's differentiate it, right? F prime of x is 3x squared. So that didn't quite work. We're close. This part matches, but this 3 here, this 3 is a problem. I don't have a coefficient of 3 in my original function. Okay, well, let's see. So that didn't work. Right? I'm going to kind of hold on to that because it was close, right? So let's see if we can try again. I'm going to let cap f of x equal x to the third, because that part was good, right? The exponent did what I wanted, but I ended up with this 3 out in front that I didn't want. So how can I adjust for that? Right, well, suppose we try this. Right, I ended up multiplying by 3 here, so suppose I divide by 3. Right, now what happens? Let's try again. F prime of x equals 3x squared divided by 3, which is x squared. That worked. Right, the derivative of this function is the original function. So this function here, cap f of x equals x to the third over 3, is an antiderivative of my original function. Now let's think about what I said there, right? Because I chose my words really carefully when I was describing it. I didn't say it's the antiderivative of the function. I said it's an antiderivative of the function. All right? In other words, there's more than one. Think about this. Think about this, and I don't want to use capital F again, but I'm going to stick with capital letters. So suppose I say g of x equals x to the third over 3 plus 1. What's the derivative of this function? Well, g prime of x is 3x squared over 3 plus the derivative of 1, that's 0. This is also x squared. All right, so this function is an antiderivative, but so is this one. And so we have a little bit of a quirk here, right? Antiderivatives are not unique, right? Because any function that you come up with, if you add a number onto the end, a constant, the derivative is still the original function. All right, so when we talk about antiderivatives, I would say the antiderivatives of this function, f of x, are the functions f of x equals x cubed over 3 plus a constant. I really want you to make a note of that. Underline it, write it in red, whatever you need to do, because this is something students trip over. It's really easy to forget to tack that constant on the end, but you're going to be doing it all the time as we're finding the antiderivatives of functions. All right, so let's see if we can generalize that and come up with kind of, I call this the power rule, right? We already have a power rule for finding the derivative of a function. So I want to try to generalize what we did on the last slide and come up with a power rule for antiderivatives, right? Well, think about what we did. As a matter of fact, let me write it over here. F of x was x squared, and cap f of x, our antiderivative, was x to the third over 3 plus a constant. All right, so what happened? The exponent went up by 1. Right, so my generalized version here, I'm going to increase the exponent by 1, and the denominator is equal to that exponent. So I'm going to divide by n plus 1. You notice how that is the exact opposite. Algebraically, it's the exact opposite of what our derivative power rule says. Our derivative power rule says you decrease the exponent. Our integral power rule says you increase it. Our derivative power rule says you multiply by the coefficient. Our integral power rule says you divide by it. And of course, remember, right, always plus a constant on the end. All right, so we've got a little more notation here. This first sentence, that's just our definition from a couple slides back. Capital F is an antiderivative of f if the derivative of capital F is lowercase f. We've got a notation for this. It's this kind of squiggly line here, right? This is the symbol for what's called an integral. Going back a couple centuries, calligraphy, fancy writing, it was kind of a stretched out capital letter I, right? That's kind of where the symbol comes from. But this is our notation. So if I want to say find the antiderivatives of f of x, that is the same thing as saying what is the integral of f of x dx. Right? So that integral sign means find the antiderivatives. So what I have here is I've just rewritten our power rule from 2 slides back using our new notation. Right? The integral of x to the n, which means find an antiderivative, find the antiderivatives, is equal to this formula. Now, before we go on, I want to make a point about this formula because there is a restriction here, right? And if you think about it for a minute, you can probably see what it is. This formula is only true for values of n not equal to -1. And hopefully you can pretty quickly see why, right? If you put -1 in here, the denominator becomes 0, which obviously isn't allowed, right? So there is that restriction there. It works for any other value, integers, decimals, fractions, the whole 9 yards, everything except that one. We will circle back to that one, right? We will fill in that gap before this chapter is over. All right, so what comes next? Well, this is going to be really the thrust of this whole chapter. We're going to spend the whole chapter talking about antiderivatives, integrals, and very briefly their applications. Integration is really the primary topic of second semester calculus, but we are going to do kind of an introduction to it here. So specifically in the next lecture, we're going to look at some more examples, right? See how you can find the integral of some specific functions.